Precalculus, continuing our little chapter 14 overview, this time with lesson 3 called Measures of Variability. So, lesson 2 was kind of analyzing stuff about what's happening with the middle of the data. Lesson 3 kind of analyzes stuff about how compact versus spread out is the data, and that can be really helpful information to know. So, 14.3 measures of variability. And the first thing is a box and whisker plot. Now, maybe you've learned about this already because of like SAT prep kind of stuff, but maybe not. It shows up quite a bit on standardized tests, I know. I would assume a bit on things like SAT and ACT. Yeah, box and whisker plot. Box and whisker plot. Box and whisker plots, or at least some variation of them, are used pretty commonly as just a quick visual way of seeing, okay, what's going on with the variability in this data, and then you can make some assumptions about how you can or cannot trust aspects of the data based on what's going on with that. So we need a set of data to work with here in order to show what's going on. And I was going to use number 9 from lesson 3 as our example. So number 9. So here's our data. We have these data points. We have 30, 28. That's a squiggly bracket, by the way, a brace. 30, 28, 24, 24, 22, 22, 21, 17, 16, 15. This is actually arranged for us just in the opposite order. That'll make it a little bit easy. Okay, so we have this data. First, what we need to find is the median. So 1, find the median. And I guess I can list this, but in the opposite order. So we had 15, 16, 17, 21, 22, 22, 24, 24, 28, and 30. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 data points. So our median is going to be the average of the middle two. 1, 2, 3, 4, 5. So the average of the middle two here is going to be 22. Okay, so then what we do is we take all of the data points below the median, which will be all of these, because the median didn't include that 22 as the average of that, and we find the median of that. So the median of that is going to be 1, 2, 3, 4, 5 is going to be 17. And then we find the median of the upper half. So we have 1, 2, 3, 4, 5 again, so it's going to be the middle one. Oops. So that would be 24. Okay. And then with this, we can find two different values. One is called the interquartile range, and the other is called the semi-interquartile range. So what we do is these medians split the data up into four quartiles. So what we have is we have quartile. So we have quartile 1. I'm going to shift that just to the side a little bit. Okay, quartile 1. And then we have quartile 2. And then here we have quartile 3. And finally we have quartile 4. And the four different quartiles of data are separated by these three quartile points. And so these quartile points we're going to call Q1, Q2, and Q3. Okay. So then the interquartile range is Q3 minus Q1. So that is 24 minus 17, which is 7. So our interquartile range for this data is 7. Then there's something called the semi-interquartile range. Oh, back to these points, I will mention this. If you have an odd number of data to begin with, let's just say we just had the numbers 1, 2, 3, 4, 5, 6, 7. 4 would be our Q2. So now below Q2 there are 3 data points, because we don't include that 4 again because we've already counted it. So then our Q1 would be the middle of what's left, and then our Q3 will be the middle of what is above. So it's almost the same, except here, because we had an even number of data points, we started out up at the top. We started out averaging the middle two to get our Q2, and then what was below was an odd number of points, so what was above was an odd number of points, so we was able to go with the middle of below and the middle of the above. Similar idea if you have an odd number of points to begin with, except your Q2 will be one of the points that will then split it into odd below and odd above again. All right, so just want to clarify that in case you run into that. Okay, semi-interquartile range is, as the name applies, half of the interquartile range. So this is 7/2, or 3.5. Okay? Then we are going to want to know a value. Hold on just one moment. Yeah, okay. So I listed the interquartile range and the semi-interquartile range because your homework problem will ask for that. The semi-interquartile range, we're not going to use as much right now. So then the box and whisker boxes from Q1 to Q2 to Q3. So that'll go like this. If we arrange our data on a number line, so if I went, let's just say we go like 10, 15, 20, 25, 30. My Q1 is at 17, so that's going to be right about 15, 16, 17. Yeah, right about there. My Q2 is at 22, so that's going to be right about there. And then my Q3 is at 24, so that's going to be right about there. So these we use as the boundaries of our boxes. Like that. And then the whiskers. Oops, I need a W. Whiskers. So whiskers, they go extend down to bottom of data and up to top unless outliers. Outliers. Outliers are 1.5 times the interquartile range below, let's say 1.5 times interquartile range or more, below Q1 or above Q3. So what I do is I take my interquartile range, this is 7, so 7, and I multiply that by 1.5, And I get 7 times 1.5 is 10.5. So an outlier will be any points that are 10.5 or more. Or is it more than 10.5? It's been just long enough since I've looked at the specific details here. Hold on a second. More than, yeah. So I should say that are more than, I should move this here, more than 1.5 times interquartile range. So our Q1 was what? Our Q1 was 17. So I go 17 minus 10.5, right? And so I'm at 6.5. So anything lower than 6.5, we won't extend the whisker to. We'll make it its own independent dot to say this is not very reliably part of the data. It's an outlier. And then anything 10.5 or more than 10.5 above Q3, which is 24. So I don't have anything that is down that low or up that high. So I don't have any outliers here. So I can just extend my whisker down to 15 here. Shink. And extend my whisker up to 30. Shink. There we go. That's my box and whisker plot. So then one thing that we can tell from this data is where is the data? How much variability is there in the data and where is there the variability? So we can tell like, things are a bit spread out here depending on the scale that you're looking at. So there's a bit of variability. The variability appears to be the most in the fourth quadrant. Quadrant 4 of the data has the, or quartile 4 has the most variability because it's the widest of the quartiles. Quartile 1 has the least variability, so the data down there is the closest together. Okay, that is a box and whisker plot. And then we move on to the big topic of mean deviation and standard deviation. Mean deviation is basically how far, so find the average of your set of data, and then find what the average distance from the average your data points are. So if your data points are all super close to the average, you would have a very, very small mean deviation because your data points on average are very close to the average. Whereas a very big mean deviation means that your data is spread out a whole bunch. And that's really important. Mean deviation and standard deviation, especially standard deviation, are really important for analyzing aspects of statistics. So our formula for mean deviation, which we can just abbreviate MD, it is this. It's 1 over n, because we're finding an average. Well, what are we finding the average of? We're finding the average, so from 1 to n of the absolute value, because absolute value speaks distance, absolute value of each data point minus the average. So data point number 1 minus the average, absolute value, finds how far from the average is data point number 1, plus how far from the average is data point number 2, plus how far from the average is data point number 3, plus etc., and then divide that by the number of data points that you have. Okay? I'm not going to take the time to do a sample problem like that for this, though. I'm going to go straight on to the standard deviation because mean deviation has certain shortcomings with ways that it can slightly misrepresent information about the data, and so standard deviation is what is much more commonly used. Standard deviation, so just like with the mean or the average, we had the population and the sample. Sigma we use for the population standard deviation. In other words, we're finding, we have all of the data points that we could possibly have for the set that we are looking at. We are not dealing with a representative sample. And then lowercase s is used for the sample standard deviation. This textbook just uses sigma, regardless of if you're dealing with population or sample. There's one difference in the formula for population standard deviation versus sample deviation. It gets into degrees of freedom, but we're not going to go. That's a relatively or a pretty complex and kind of in-depth topic that we are not going to touch. So standard deviation, here's what we get. We get sigma equals, now check this out. I'm going to basically take my formula that I started with, but just put it inside of inside of a square root. I just made that a little bit bigger than what I needed to. Inside of a square root, and I still have my 1 over n. I still have my sum from I equals 1 to n. But now, instead of absolute value, it's going to be parentheses x sub I minus x bar, and parentheses squared. So it's nearly the same thing, just a little bit different. So we can do one like this. Oh, and then actually, before I go on to that, let me say one other thing. Variance is just sigma squared. So what sigma squared is this same formula, just get rid of the square root. So it's just the 1 over n times the sum from I equals 1 to n of each data point minus the average squared. Just add up those squares and divide by how many data points you're dealing with. So our sample problem here is number 13. And this is find the find the mean deviation and the standard deviation. So mean deviation and standard deviation. Find MD and sigma. Of what data set are we dealing with here? We are dealing with 200, 476, 721, 579, 152, and 158. Okay, so first we have to find the average. So first find x bar, because we need that for these calculations. So we're just going to add up all these and divide by 1, 2, 3, 4, 5, 6, divide by 6. So I add them 200 plus 476 plus 721 plus 579 plus 152 plus 158 is 2286. Divided by 6, and let's see what I get there. We get 381. Okay, so now the mean deviation, I'm going to do 1/6 times each one of these data points, absolute value of each one of these data points minus the average. So times absolute value of 200 minus 381 plus absolute value of 476 minus 381 plus absolute value of 721 minus 381 plus absolute value of 579 minus 381 plus absolute value of 152 minus 381 plus absolute value of 158 minus 381. You can tell this gets tedious. Very, 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 very infrequently is statistics done by hand. You almost always what's done is you have databases, Excel spreadsheets, text files with rows and columns of data, and you use computer software to do all of these calculations for you just in the blink of an eye. Yeah, I'm not going to take the time to manually calculate this out. Personally, I wouldn't bother with the absolute value. I would just, if my value was smaller than the, like when I calculate this on a calculator, if my data point is smaller than the average, then I do the average minus the data point. So I do 381 minus 200 plus 476 minus 381 plus, and then when I got to like the 152 plus 381 minus 152, that way it is accomplishing the same thing as if I had been dealing with the absolute value. So when all is said and done, what do we get here? We would get 211. And then sigma would be the same thing, but I'd go inside square root. I do 1/6 times, and it would be 200 minus 381 squared plus 476 minus 381 squared plus, and it's all of this inside the square root. Dot, dot, dot. And what you should get here is about approximately 223.14. Okay? So that is mean deviation and standard deviation. And again, what it's showing you is how close to versus how far. So let's look at our mean deviation here. A mean deviation of 211. So what that tells us is our average is 381. But then on average, how far away from 381 is our data points? Well, the average distance away from the average is 211. If the average is 381 and my data points distance away from that is on average 211, that tells me that data is pretty well spread out. That is kind of all over the place. Not super all over the place, but that's some pretty spread out data. That's not that my data points are not tending to be very close to the average. They're tending to be spread out quite a ways. Okay? All right, so that is our lesson 3 kind of stuff. And then we'll do just, yeah, a little bit with lesson 4, maybe with lesson 5. I'll have to decide. Largely is based on looking at the lengths of these because they're not going quite as quickly as I had hoped, but also not going super long, so we'll see.